My name is Nielsen, and this is an introduction to grammar and parsing using the Recursive Descent Parser algorithm. In this talk, we are going to see basic definitions of parsing and grammar and what's the Backus-Naur form. And we'll see how the abstract descent parser works, implementing one in JavaScript. So what is parsing? It is also known as syntactic analysis, and it means reading input while understanding what it means and converting it into a more useful format. Let's take, for instance, a JSON parser. So a JSON parser taking this string as input would understand it as an object with a property called ID with value 1. So parsing is understanding according to a grammar. The JSON parser, for instance, understands the JSON grammar. And what's a grammar? It's a set of rules that describe how to form strings that are valid according to the language syntax. The JSON grammar, for instance, has this rule. I took this from the json.org site. So an object begins with left brace and ends with right brace. It has an unordered set of name-value pairs, and each name is followed by a column, and the name-value pairs are separated by comma. How can we describe rules like that in a more formal way? Well, enters the Backus-Naur form. The Backus-Naur form is formed by terminal symbols, non-terminal symbols, a start symbol, and one of the non-terminal symbols is the start symbol. It has a set of productions, and each production has a non-terminal on the left side of it and a sequence of symbols on the right side. And it has meta symbols. The small letter epsilon means empty, and the vertical bar means or. Let's see, for instance, this example. This is a grammar for balanced parentheses. So we have s as our non-terminal, and we have two rules for s here. S is also our start symbol. The first rule says that S is defined by open parentheses, S close parentheses. And those two, open parentheses and close parentheses, are terminal symbols. The second rule says that S is defined by empty. We can rewrite those two rules as this. S is defined by open parentheses, S close parentheses, or empty. So valid inputs according to this grammar are checked by starting at the start symbol and applying the production rules. So open parentheses, close parentheses can be checked by starting with S, applying the first rule, so we have open parentheses, S, close parentheses, and applying the second rule, replacing this S by empty. An input like this would be matched by starting with the start symbol, applying the first rule, open parentheses, S, close parentheses, replacing this S again using the first rule, so we would have one more open parentheses, S, close parentheses in the middle, and then applying the last rule here and changing S to empty. Let's move now to a grammar for mathematical expressions, and we will start with a fully parentized expression grammar. So here we have our expr rule that defines expr as number or open parentheses expr operator expr close parentheses, and operator and number are terminal symbols defined by regular expressions here. So operator is any of plus, minus, multiplication, or division sign, and number is a digit one or more times. Valid expressions according to this grammar. A number is a valid expression. We can replace expr by a number, applying the first rule of expr. This is also a valid expression. We can, starting with expr, apply the second rule, open parenthesis expr operator expr close parenthesis, replace the first expr by a number, and replace the next expr by a number again. Let's check this more complex expression now. Starting with expr, we apply the second rule, open parenthesis expr operator expr close parenthesis. We replace expr by a number. We apply the second rule again here, so replacing this expr by open parenthesis expr operator expr close parenthesis. We replace the first expr by a number, and we replace the next expr by a number. We can represent this sequence of rules by a tree. So this is a parse tree, also known as a concrete syntax tree. It's a tree that represents the syntactic structure of the string according to a grammar. The root of the tree is always the start symbol, and the leaves are the terminal symbols. Let's try to change now our grammar to match expressions without parentheses. And we'll start by just removing the parentheses from the grammar. We could match this input by a tree like this. So we would apply expr, operator expr here. And the first expr would be replaced by a number, and the second one again by expr, operator expr, and each expr by a number. But we could also have this tree if we applied the rules in a different order. So we here, instead of applying the first rule, apply the second rule, we would have this, and then we would apply the first rule here. So grammars that can generate different parse trees for the same input are known as ambiguous grammars. Quiz. Which inputs are valid according to the grammar defined below? S defined by A, and A is a terminal symbol, so S defined by AT, and T defined by BT or empty. Which are valid? A, B, AB, ABBB, ABBA. The answer is A, AB, and ABBB are valid. This is because this is a grammar for one A and 0 or more Bs. Let's apply a structure like this to our grammar to remove the ambiguity from it. So we would rewrite it using two non-terminals. Expr, defined by number expr prime, and expr prime defined by operator number expr prime or empty. So with a grammar like this, we would have number and 0 or more operator number repeated. Let's test it with this input, starting with expr, and when we have more than one terminal symbol, the first one appearing, so the first rule defines the start symbol. So our start symbol here is expr. We apply its rule, replacing it by number expr prime. We then apply the expr prime rule, replacing it by operator number expr prime. We apply the expr prime rule again, replacing it by operator number expr prime. And then we apply the second expr prime rule, replacing it by empty. This can be rewritten using extended BNF as this: expr defined by number, and then between parentheses operator number, and then a star. This is extended BNF, and we'll be using it from now on. Let's further change our grammar to be able to recognize inputs like this. So inputs with parentheses just when needed. And let's say we also want to have operator precedence, so the multiplication operation would have higher precedence than the subtraction. We start by replacing number by a new non-terminal symbol called factor. We add open parenthesis expr close parenthesis as a second rule for factor, so we can match it here. We then create a new non-terminal called term and add it here. And then we split our operators here. So expr matches plus and minus, and term matches the multiplication and division signs. Let's see how it works with this input in the parse tree. So expr matches term because we can have this 0 or more times, so expr is also a term. And we match here term as factor, division sign, factor. This factor is matched as a number. This factor is matched as open parenthesis, expr, close parenthesis, which is the second rule for factor. Then this expr is replaced by term minus term. This term is replaced by factor and by number, because we can have term just being a factor with this is repeated 0 or more times. And here this term is replaced by factor times factor, and each factor replaced by a number. Let's now see the recursive descent parser algorithm. It is a top-bottom, left-to-right algorithm, meaning it analyzes the tree from top to bottom, from the start symbol to the terminal symbols, and it analyzes the rules from left to right. It doesn't support left recursion, and left recursion is when, for the definition of a non-terminal, we have it as the first symbol in the sequence of symbols of the rule. We can't have even left recursion in more than one step. This is not allowed in the recursive descent parser algorithm either. So for this grammar, for example, we can replace expr by terms plus term, and we can replace term by expr times expr. So this would give us expr here, and we started with expr. So this would, for the recursive descent parser, give an infinite loop, because the recursive descent parser always tries to replace the first non-terminal it finds until it reaches a terminal. So this wouldn't happen here. Let's see it working in that grammar we just defined. So we start with our start symbol, and we have an index pointer pointing to the first position in the input. We start the expr rule, and think of rules as functions. So think of each non-terminal as a function. So when trying to match term, we'll actually call the term function. So we start the term rule here, and term has to match a factor. We start the factor rule, trying to match a number, and we matched. As we match, we are done here, and we go back to our term, and we try to match the next symbol we have, which is the multiplication sign. We don't match, and since we are inside an OR part of the rule, we backtrack, and we try the next option we have, which is the division sign. We try the division sign and fail again. But as we are inside an OR here, because remember, the 0 or more construction in B and F has an OR and an OR empty. So actually, we backtrack here, and we can match empty. It's valid. We can match 0 times. So we backtrack. We are done here. We go back to our expr rule, and we try to match the next symbol, the plus sign. We fail, but we are inside an OR, so we backtrack. We try the next symbol, the minus sign, and we matched. So since we matched, we go to the next symbol. In term, we start the term rule. We try the match factor. We try the first part of the factor rule, or the first rule factor, and we match number, and we succeeded there. So we are done with our factor. We try the next symbol, the multiplication sign. We matched it. So we go to the next symbol, which is the factor. We start the factor rule. We match the number. We are done with our factor. And as we are inside the 0 or more here, we'll try again. So we'll try to match a multiplication symbol again. We fail because we are past the input, but we are inside an OR, so we'll try the next option. We'll try the division. We fail. We are done here with our repetition. We are done with our term. We'll try to match this part again because we are inside a 0 or more. We'll try to match the plus. We are past the input. We'll try to match the minus. We are past the input. We are done here, and we match the expression. Quiz. An abstract descent parser implementing the grammar we just saw parses the input 5 minus 2 times open parentheses. So this is actually the same input we had in our test before, but with an open parenthesis at the end instead of a number. So where will the parser position in the input be after parsing finishes? Mind backtracking. The answer is at the multiplication sign. This is because it would try to match a factor here because of this open parenthesis. It would try the second rule. It would fail because it would expect an expr here and it wouldn't match anything. So it would fail, and it would go back to our term rule, and it would backtrack everything here because remember that the 0 or more construction in BNF is like this. So actually, when we fail our factor here, we backtrack everything we have inside the rule. So we backtrack before this multiplication sign we matched here. So our valid input for this is 5 minus 2. It recognizes this part of the input. Let's see the implementation now. So as I said, each production rule is implemented as a function, and we backtrack when there's an OR. So for a production rule with a sequence of symbols, let's say, for instance, S defined by S1, S2, and which each one of these are non-terminals, so they are functions here. So S would be defined by this function. It is a function that returns a call to S1 and S2. So what happens here is if S1 fails, it returns false. If S1 succeeds, it tries and calls S2. If S2 fails, it returns false. If S1 succeeds, it returns true. Now for a rule with OR, let's say T defined by T1 or T2, and T1 and T2 are also non-terminal symbols, so they are functions. And we have to backtrack here. So this would be an implementation. We save our index, so index is the current position in the parser. We save it in a backtrack variable, for instance. We call T1. If T1 succeeds, we return true. But if T1 fails, we backtrack, so we set index back to that backtrack variable we saved, and we call T2. If T2 succeeds, we return true. If T2 fails, we backtrack again, so we set index to the variable we saved before calling any of these functions, and we return false because we failed. We need a last function to match terminal characters, so I'm defining here a char function that receives a expected character as parameter. It tests if it's not past the input and gets the character at the index position of the input and tests if it's equal the expected value passed by parameter. And we can increment index here after getting the character because we will backtrack anyway. So it's safe to do this, even if we don't match. And the usage of this function would be like this. So if we had a rule S defined by the terminal A, we would call it like this. We would define it like this, implement it like return char of A. So let's move now to coding. So I have some unit tests here. And so I defined them by putting some garbage at the end of the inputs. So for this one, I wanted to match just the numbers, this open parenthesis garbage. So I'm doing this to make sure the match returns should return only the matched part, the valid part of the input. The same here, and the same for the rest. For instance, here I'm putting 4 characters of garbage at the end. The same here, 4 characters that I don't want it to match. I have this test page here. Actually, now it returns the input. So it is returning the input. Anything I type here, it accepts. So we will implement now the correct implementation for matching inputs. So I started with what we saw. We have the char function here. I added a regexp function to match regular expression. So I pass a regular expression as parameter, and it will return true if it matches, and increment the index by the number of characters matched. And I'm using it here in my number function. So I'm matching here. This is a little bit more complex than what I showed in the presentation. So this matches a digit 1 or more times, and it has a non-catching group here, optional, that can be matched 0 or 1 time with a dot, a point, and 1 or more digits. So let's start implementing the factor rule. I will split it with 2 functions. So the first function would match number. Whoops. And the second function matches our sequence of symbols there. So we have char open parenthesis, the terminal symbol, expr, our non-terminal, which is a function that we will implement later, and our terminal close parenthesis. So that's what we want to return. And the factor implementation would be, and I will create a helper function called firstoff that receives many functions as parameter and does the backtrack as necessary. So this is our OR implementation. Let's do it here. Firstoff is a function. It will receive many arguments, and I will loop through the arguments like this. and we will call each argument, so the ith argument will be called here. And what we want to do is, if this call succeeds, we want to return true. If none of them succeeds, we return false. And we want to do the backtracking. So we do it, we save it here. And if it fails, we restore the index value that we had before calling any function. So this should do it. Our factor rule is ready. Now let's move to the term function, to the term rule. So this would return factor. And now I'll create another helper function here, 0 or more, that also takes a function as argument, but actually this one takes only one function as argument. And this function here would be what we have inside the 0 or more in our rule, which is matching times or division sign. I would do this using the regular expression. So is any of multiplication or division. And we have to match the factor here. So let's implement the 0 or more. It is a function that receives just one function as parameter. We want an infinite loop here. I like to write it like this. And in our infinite loop, we will be calling our function past this parameter. And what we want to do here is, if it fails, so if not func, we want to return true. We want to return true because matching 0 times is valid. So we can match, so it always returns true. This is like, return true is the rule for empty actually. It's the implementation for empty. And we want to backtrack. So we want to backtrack. Here we want to save the position before calling func. And we will backtrack here. So after func fails, we set index to the value you saved before the last call to the function. So we are done with our 0 or more. Let me fill this. So our term rules should be ready. Now let's do it for the expr rule. We call term. We have a sequence of term and 0 or more, and a function inside 0 or more that evaluates a plus or a minus sign. I will do that using regular expression again. So here we can have any of plus or minus. And after matching that, we want to match a term. Good. I guess we are done here. So now we have to change this. So this is returning input. This is what we saw on that web page. Actually, what we want to do is, well, we want to call expr. And if expr succeeds, we want to return just the part of the input that it matched, which is starting from 0 until our index pointer. If expr fails, we want to return null. Good. Let's run our unit tests. Good. We succeeded. Let's see how that web page now works. So If I do this, it won't match. Actually, it matches when it's complete. For instance, if I put a lot of parentheses here, it will only match when the parentheses match. So that's it. It also matches numbers with dot. See that the dot only appears when the number is complete. So good. Now let's improve our code by making it actually do the calculations. So I will enable those unit tests here that I had disabled before. So this actually tests if the parser now is able to do the calculation and return the right result. So what we have to do here is first change our char and regapps functions. So we want our char function to return the matched char. So let's do this. We save the matched character here. And if this is true, we return the matched char. Otherwise, we return no. Our regexp, we wanted to return a match. Let's move here, change here to no too. Our first off rule, we wanted to actually return the value returned by the first successful function called. So what we do is we save the value here. If vol is true, we return it. Otherwise, we return no. Well, the 0 or more will be the same. We can't aggregate all the results in the return value of it. Now let's go to our number rule here. So what I want is this returns actually regexp returns a string. So what we want to do is, if the string is not empty, we want to convert the string to a number. Otherwise, we return no. And actually, I'll need another helper function here, because the number 0 is falsy in JavaScript. So we need to convert it to truthy. So we do that. We can do that like this. We return vol if it's truthy, or new number 0. So we create an object number 0. So objects are truthy. Now we want our number function to use this. Now let's move on to our factor rule. So here we want to return the value that was returned by expr. So we save it here, and if all this is true, we return vol. Otherwise, we return no. Our factor1 number returns number, which is already what we want. The first off, we return the first valid thing here, which is also what we want. Now, our term function, we want to keep the left var as the return from the factor call. And inside our 0 or more function, we want to test for up, for the operation, and we want the right value. So up will be the result of our regular expression call, and the right val will be the result of our factor call. And, well, what we want to do here is we want to test here. So if this is true, we want to do something here and return true. Otherwise, we will return false. And what we want to do here is switch by our operator. If the operator is the times operator, we will update our left var. I guess I called left var here, but I want to call it left val. So we will multiply itself to right val. Break out of the switch case. And if it's a division sign, you want to update left val by dividing itself by right val. Break. And what we want to do here is return. So if this is valid, we want to return left val. Otherwise, we want to return no. And we must make sure our left val is truthy. So we use our helper function, that one we just created. And let's do the same for expr. It's almost the same implementation. We save our left val here. It is the return of term. Inside of our 0 or more, we want up and right val. Up will be the return of the regular expression, and right val will be the return of the term. We want to test this. So if this is valid, we want to return true. Otherwise, we return false. We want to switch again according to the operator we got. So if we got the plus operator, we will update our left val, summing it to right val. Break. And for the minus operation, we'll do the same. Actually, this logic is if left val, so if 0 or more is evaluated 0 times, left val would have our term, so we would return it. Otherwise, if we have a operator and term, so what we want to do is update the left val with the operation on left val and right val. And this would work also if we have more than, let's say, 2 or more repetitions inside our 0 or more. So here we want to return left val as a truthy number, or null. I think we are ready. Let's run our unit tests. Oh, I guess I missed something here. Oh. Okay, so actually I forgot to implement the parse function. The parse function, as we'll see here on the spec, it returns an object with a result property with the result. And we want to keep our match function working. So we'll do this. So this will be our parse function. We'll still have a match function, and what we want the parse function to do is call expr. So now expr gives us the result. We'll test for the result here. So if the result is truthy, we want to return an object containing the result as a property. And let's return also a property called match with the matched input here. And our match function would call the parse function, passing the input, and if it returned a valid object, not null, we would return parse.match. Otherwise, we would return null. Now let's go to our unit tests. I guess I missed something here. What's that? Oh, I want to return this. Good. Our test passed. Let's see it working in our page. So here it is. So this code actually shows the matched input and the result. So if we have a lot of garbage at the end, it won't match until we have the right number of parentheses. So good. Now I added this code I just created to GitHub, so you can visit github.com/ericbn/js abstract descent parser. I left there a few links, like a link to an online course on compilers that covers this subject if you want to see further. Also a reference to a classic book on this subject, and a few challenges for you. So actually 3 challenges. Thank you.